So this is going to be the last video of section 3.1, and we're looking at how to not only find the rate, but also predict the original amount given the number that we have currently. So or we could also find, um, using the graph, we could also find the time or anything else that we would want to know given these functions. So looking at this example here, we have a table showing the population growth between 2000 and 2010 of deer. You can see in 2000 there were 125, and 2010 there were 264. Now we're going to assume exponential increase here, and what they're asking for is the rate and also a model to represent this situation. So we're going to use what we have been using. The number of deer is equal to the original number times 1 plus that rate to the time power. And we know that um, between 10 years, so the current population is 264. The original one was 125. We're trying to find that rate, and we know that the time between these two is 10 years. So we're going to go ahead and throw in 10 for t. So now it's just a little bit of algebra to solve for r. Um, we're going to divide both sides by 125. So we get 264 over 125, which is 2.112 equals 1 plus r to the 10th power. Now what we're going to do is take the 10th root. Probably don't do that very often, but we're going to take the 10th root of both sides to get rid of that power. The 10th root of um, 2.112, we can just go ahead and take that to the 1/10th power. That's essentially the same thing, if you recall how to use fractional exponents. So 2.112 to the 1/10th power is 1.078. So 1.078 equals 1 plus r. So then we subtract 1 from both sides. We get 0.078 is equal to r. Good thing it became under 1, because we can't have well, we could have a rate of over 1, I guess. You could have something increasing at like 200%, but just to think of it reasonably, a rate around here is good. So, in other words, that's a 7.8% increase. To write an exponential equation to model this, we could write 264, or actually, let me erase that real quick. What I want to do is leave it open to figure out. So, the number of deer is given by our original number, 125, times 1 plus 0.078 to the t power. That way, we have a function that gives us the number of deer depending on the time we have. Now, part B asks us to use this growth model we came up with and predict how many years it'll take for the number of deer to reach 500. So we want this n value here as a function of time to reach 500. So let's go ahead and graph this function we came up with. Clear my old functions here. And we have this function is equal to 125 times 1 plus 0.078. That's going to be taken to our variable power. Obviously, it's the t power, but that's our independent variable in this case. So we're just going to use x in our calculator. Let's zoom and make this fit. I'm going to use 0. There we go. Taking a little while to graph, but there's what our function looks like. And we want to know when the number will be 500. So if we trace this here, let me make this a little bigger, hopefully, so you can see it. Um, so we're at 125 now when time is 0. And we can kind of trace it along there, increasing. Sorry, it's taking a while here to get to 500, but I'm just looking for when this y value reaches 500. We're at about 300 now, and keep tracing, almost there. Looks like maybe between the year 18.3 years and 18.5 years, somewhere right in the middle there. So I'm going to say about 18.4 years, roughly. That's my best estimate. I can probably zoom in and go even better than that, but I'm going to say time is about 18.4 years. And if you wanted to, you could check that in your model. If you just throw in time for, uh, or 18.4 for your time up here, and then take 125 times 1 plus 0.078 to that power, you should get around 500 a year. So here's an example for you to try, see if you can model this growth rate of the rabbit population.